Fantastic. So, as I mentioned really quick from the comments before, we've made a slight change. The talk that was originally scheduled for 11:30 is going to be bumped to after the break this afternoon. The online agenda should be updated shortly. They're tying into that, there's a couple issues with the website right now, and they're actively working on fixing that. And so if you try to go to it, doesn't load, give it a couple minutes, and the squirrels that are rebooting it will have probably rebooted it at that point. So for our last talk before lunch, I'd like to invite Benjamin Vick up to talk about 100 gig deployment at Comcast. I know that us at Netflix have recently deployed 100 gig. It's certainly interesting to hear how others are using it, where they can find cost efficiencies and where it makes sense from a technology perspective. So, Benjamin.
Good morning, everybody. My name is Benjamin Vick. I'm a transport engineer for Comcast. I just wanted to thank everyone for giving me the opportunity to get up here and speak about this. It's not every day that we get to talk about our networks in such an open forum, so I think that that's, it's very exciting to have that opportunity to discuss it. My goal here today is really to discuss some of the challenges that we've had developing this network. It's been a long process, and it's a very large-scale network, so some of the challenges that we've been through are pretty unique. The network itself is currently made up of about 58,000 route kilometers of fiber. We've got over 450 physical sites, and we've got over 1,200 transponder and photonic shelves. And when I look at that number, it's pretty significant in that in dealing with our equipment vendor, it's such a large-scale network that from a scalability standpoint, it almost turns into a partnership with them. This network is large enough that when we have scalability issues, they're learning those same lessons right alongside of us. It's not a situation where we can call them and say, hey, we saw this issue, and they go, yeah, we've seen that before, here's how you fix it, and so on and so forth. We're really learning these things together. The network is, it's a transport network, so I wanted to talk about the wavelength breakout. We've got, our core network is N by 100, so every core-to-core link is at least 1 by 100, if not much more than that. We still have 40 gigs that go from the core network out to the edge, and we still have a small amount of inter-regional 10 gig links. And the reason this is kind of important is that the network that we're running, it's a transport network that's a production network running 10 gig, 40 gig, and 100 gig, all in the same spectrum space. And that in and of itself leads to, some scale issues that we can get into. So just to give you guys an idea, this is just a quick map of the network itself. It's a national network. It's our backbone network. And as you can see from the picture, it's a relatively large network. This is not a small network. This is a very large network with unique issues. I wanted to just quickly touch upon some of the terminology related to DWDM, just so that everyone was on the same page as I talk through some of these things. Pretty much in a DWDM system, you've got a router that interfaces with a transponder. What we call that is it's a gray light connection. From that gray light connection from the router, you then have a transponder that changes that into a colored wavelength that follows the ITU grid. From this ITU grid colored wavelength, we come into an optical filter. This filter is responsible for combining or multiplexing multiple wavelengths from multiple transponders and then feeding those wavelengths into what is called a wavelength selective switch. The wavelength selective switch basically determines which direction you're going to leave your DWDM site on. So from this switch, you then have multiple wavelengths combined onto a single pair of fiber that head into an amplifier, and that amplifier then leaves the site and sends the wavelengths down that pair of fiber to the next site. Usually in a long haul application, that next site's going to be an inline amplifier site. So this site is basically just responsible for amplifying the wavelengths and continuing to send them on down the line. In a long haul situation, you'll have multiple amplifier sites before you hit your next ROADM site, which is a reconfigurable optical add-drop muxing site. Again, this site has basically two responsibilities. It either is going to break out the wavelengths, send them into a transponder which will terminate on a router, or it will reroute the wavelengths in a different direction and send them on a new path to their next ROADM site. So our backbone network is basically responsible for a couple of types of traffic. Primarily, its responsibility is to carry traffic from between our different regional networks. We also carry traffic from the backbone into and out of our internal data centers, and we also handle edge connections with our external partners as well. So here we go. I mean, this was pretty much the start of the network. 2003, 2004, we started the idea. This was really the design phase. So to start the design, we had to consider fiber. And as you can see on this list here, there's multiple types of single mode fiber that make up our backbone network. Unfortunately, in a national network scenario like this, you don't really have as much control over the fiber that you would in a smaller metro network. And so you have to kind of take pieces here and there and take what's available. And that, it makes it really important that your network is robust, because all of these different types of fibers have different characteristics, have different strengths, different weaknesses, and you need to be able to put your network on all of them across the board. In our design phase, we basically chose Nortel, now Ciena, as our equipment vendor. At the time, they were taking a little bit of a chance and deviating from what was the commonplace DWDM architecture by using an electronic dispersion compensating transponder. At the time, the norm was to use a fiber-based dispersion compensation unit, which was just a module that had a spool of fiber in it. You racked it in a rack, you connected it to your amplifiers, and that was the process. It was very static. If your fiber characteristics changed, you would have to swap out the modules. It was a major maintenance. The solution that Ciena was developing was one that was very dynamic. It could handle changes in the fiber characterizations, and so it really could change things on the fly. So to us, that was a very interesting thing to have as a technology. But the other thing that was extremely important to us was their promise of coherent receivers in transponders. And what the coherent transceivers offered in the future was going to be basically a uniform performance level across all of these multiple types of fiber. So as a large national network, that's really what you're looking for. You want everything to kind of look the same and feel the same across your network. So when you're in California and you've got a certain type of fiber, and you're in Boston with another type of fiber, your transponders are doing the same thing, and that was extremely important. The other thing that the coherent receivers were going to provide to us in the future was their ability to handle different modulation schemes. And what these modulation schemes were going to allow for was increased data rates. So building our network at 10 gig initially, we knew that we were going to grow. We knew that we needed to have a path for growth, and having a coherent receiver that could push 40 gig, that could push 100 gig, those were promises of the future that we really wanted to sort of take them up on and see where it led to. So once we had figured out what our design was going to be, we basically then needed to build it, right? So day one, the network had over 30,000 route kilometers of fiber to start. And again, this is multiple long-haul dark fiber providers, and as well as some of our own internal fiber in more of our regional local market level. Our co-location facilities were made up of three main types. We would use third-party sites for our core gateway nodes, our AMP sites, and our smaller ROADM sites. We used our own Comcast-owned facilities as our regional touch points. And then, like everyone else, we were using carrier-neutral facilities for all of our edge connections. The network at that point in time, even day one, had over 500 shelves in the network that made up the solution. So once we were done building out the full backbone, we had all of our sites fired up and ready to go, we then needed to put services on it. Day one, we started with 2 by 10 gig on all core-to-core links. So these are our major core sites from site to site. We also had 1 by 10 gig from our core into our regional networks. And while there's not as much bandwidth from our core to our regional, I would like you to think of those as kind of like a highway off-ramp. So there's not as much bandwidth there, but they're heavily utilized links because that allows us to push our data from the backbone down into these smaller regional networks. And so with that initial deployment, we sort of immediately started seeing rapid growth, and we knew quickly that it was going to be paramount that this network could scale. And so to give you an idea of why scalability was so important, I wanted to pull up this slide. So you see the two stars, one is relatively in New York, one looks like it's in Chicago. This was a core-to-core link for us. So New York to Chicago is a core link. It travels from New York up through Boston, through Canada, back down, around, and into Chicago. This core-to-core link is made up of over 30 individual spans. And so when you look at 10 gig and you say, well, 2 by 10 gig doesn't seem like it's the most amount of bandwidth out there. You have to keep in mind that for us to deliver a single 10 gig from New York to Chicago when we first built this network, it took 10 transponder cards. So day one, our initial 2 by 10 gig deployment used 20 transponder cards just for two 10 gig circuits. Quickly after deploying that 2 by 10 gig, we needed 4 by 10 gig. So you've now added an additional 20 cards to your network. Within a year of deploying that, it was time for 8 by 10 gig. So now you've got 80 transponder cards for 8 10 gig circuits. And when you get into this level of cards for this amount of circuits, you start to realize we can't continue to scale this way. With too many cards, you start introducing the possibilities of card failures. With all of the regen locations, you've got more and more fiber connections that, again, you run the risk of a hands in the plant type accident that could be a service affecting outage. And so we knew very quickly and very early on we needed a scalable solution. So we were already pushing the vendors very hard for the 40 gig implementation that they were working on. Since the electronic dispersion compensating transponders was relatively new and we were taking a chance on it, we kind of wanted to cover ourselves as well and have a plan B. So with that, what we did is we actually deployed the fiber network with the traditional fiber-based dispersion compensation modules in the network and then used the electronic dispersion compensating transponders on top of that. We actually lucked out, and it turned out that the transponders themselves worked, and they worked really well. Really, the only issue that we had with it was that the fiber-based dispersion compensating modules were hampering the performance of our transponders, and so it was something that we were going to have to deal with at a later date. When we look at a network, when we look at any of our build-outs, when we look at technology, we always kind of set a goal to future-proof things. And I mean, as anybody knows, I think it's pretty impossible to completely future-proof any network, but it's always the goal to make sure that you're in a good position, 4 or 5 years down the road. One of the things that we had initially built into the network were modules called C and L band splitters. Basically, the thinking was if we use C-band and we fill it all up and use all of those channels, we're in a good position to simply add L-band filters in line, and we can quickly and easily add spectrum. Turned out that L-band never really materialized, and nothing really happened with it, so it was one of those things that it went unused in the network. Another future-proofing plan that we made was to target spans for Raman amplification. Basically, we were targeting our longer spans, our greater loss spans, and some of the spans that had fiber that wasn't really the greatest fiber to be using for DWDM applications. So in 2006, that really is kind of the next phase of the network for us. We start to see that it's time to go to 40 gigs, so we're making the transition. We start upgrading all of our core to be N by 40 gig at that point in time. Like I said previously, we had targeted spans for Raman amplification, and just kind of a quick aside, the biggest difference in amplification, standard amplification like an EDFA, basically amplifies your wavelengths in the same direction that they travel, And the difference between that and a Raman amplifier is that the Raman actually sends a highly amplified wavelength the opposite direction. And what this does is this causes the power levels of all the wavelengths traveling along the fiber to be increased and elevated. And that really gives you two benefits. Number one, it increases your reach. So now you can take out regens if you had them, and you can go longer distances. The other big major benefactor of that is that you the Raman amplifier increases your optical signal to noise ratio, which is basically a ratio of the noise level to the actual optical signal itself. And so the greater distance you can put between the two of those things, the easier it is for your transponders to receive the signal correctly, the less errors it causes, and the cleaner your signal is overall. So those were really two great benefits to the Raman amplifiers, and so as we targeted those spans, we really started to put them out there. Also in 2008, we were the first network to perform a 100 gig trial. And the thing that made it unique was that this was a 100 gig trial in a mixed transport environment. And what I mean by that is that this was a network that carried 10 gig waves, some 40 gig waves, and then the 100 gig wave as the trial as well. And the reason that this is important is because you need to understand that with all of these different bandwidths, all these different transponders, they're all running different modulation schemes, and those modulation schemes react differently to the nonlinear characteristics of all the fibers. And so when you've got different fibers and different modulation schemes all playing together in the same sandbox, it can make things difficult if the hardware is not capable, if the network's not designed correctly. So for us to be able to trial 100 gig in that mixed environment was a very big deal. This 100 gig trial was also more than just a proof of concept for us. This was going to be the future. So when we did this 100 gig trial, we really were looking to learn lessons. We were really looking to figure out what we needed to do to the network in order for us to move to 100 gig and move there smoothly. We didn't want to wait till we rolled it out to figure out that we needed to change things. That would have been too late. So it was a great opportunity to make sure that the network was going to be prepared for all the different changes that we needed to make to it. So our 40 gig deployment in this 2006 to 2009 timeframe, it was really broken into two phases. In 2006, we were really ready for 40 gig. However, our equipment vendor wasn't quite ready with their 40 gig transponder. And what that did is that pushed us in the direction of integrated optics. And so what integrated optics were at the time is basically there was a hardware vendor that was integrating wavelength capabilities into router interfaces. And so this allowed you to skip or bypass the transponder and go directly into your optical filter and then down on the line. And this was a good solution as sort of a stopgap for the time because we really didn't have a 40 gig transponder to use. However, it did present some challenges. The first and foremost challenge was reach. We really were not getting the reach that we were used to on the 10 gig scale out of these integrated optics on the 40 gig level. And what that really pushed us to is we then needed to add regens into the network to carry these 40 gig channels from core to core. And so you're incurring more costs, you're incurring more complexity into the network. And that really wasn't a direction we necessarily wanted to head in, but it was something we needed to do because the bandwidth demand was there. The other difficulty in adding those regens at the time is that the manufacturer of the integrated optics really was trying to do just that, integrated optics. They weren't a transport vendor, and so they really didn't have their own shelves or cards or boxes to make as regens. So we kind of had to work with them hand in hand to get those boxes created for our purposes so that we would have regens and be able to get these 40 gig links up and running, which was extremely important. And so at that time, in that sort of 2006, 2008 timeframe, the network is really expanding quite rapidly. And in 2008, our hardware vendor had come out with their 40 gig transponder solution. And this was a coherent receiver, 40 gig transponder, and it was basically what we had been looking for, but we were caught in a tough position because the coherent receiver was not going to work well with the fiber-based dispersion compensation we had in the network. and the integrated optics wouldn't work without them. So basically we were in a catch-22 where we needed them for the existing infrastructure and we needed to pull the dispersion compensation modules out for the future infrastructure. So there was kind of a changing of the guard when we switched to the 40 gig transponder solution away from the integrated optics. Now, one side note I wanted to mention is that the integrated optics of 2006 are not what they are now, and so it's still a viable solution. It's still something that is on the table for us, that we look at the network and look for areas that we can integrate it back in. It's just that at that time, it really wasn't quite the perfect solution that we had hoped it had been. And so as the network grew, we really knew it was time to advance. And as you'll see in this next slide, I can point to really where this was going. So as you look at this slide, this is a graph of bandwidth just on one of our sample long-haul spans. And really, as you can see in 2009, we're ready for 100 gig at that point. At that point, this sample span, for example, was 8 by 40. And again, we started running into the same issues we were having with the 10 gig network, right? The scalability issues. When you're 8 by 40, you have those scalability issues that you really want to push to the next level, which was 100 gig for us. As a quick aside, looking at this graph, you can see in 2013, we are currently at 14 by 100 on this span. So when we talk in the future about 400 gig and terabit and what the next path will be, if today terabit was available, on just this span alone, we would need 2 terabit channels to handle the traffic. And so we very much are pushing for the future, and we're ready for that change to happen. So I mean, we've talked to a lot of people and we've heard a lot of things, but right now we're ready for that terabit solution, and you can see that we're still pushing even today in this network growth area. And so coming up on 2010, we were starting to, really move forward, and we understood that 100 gig was now something that was going to be here soon. And the lessons that we had learned during the 100 gig trial were really things that we needed to put into practice now in order to be ready. We didn't deploy 100 gig wide scale across the network until 2012, and so before that, it was really time to clean up the network. So we knew from our 100 gig trial that we were not going to be able to have the fiber-based dispersion compensation modules in the network. So that meant we needed to pull all of those out, which also meant we needed to fully remove any of the integrated optics from the network, because without the dispersion compensation, they weren't going to work as well. So that started really a 2-year process to get those out. I mean, this was a site-by-site maintenance project that it took about 2 years to get through, removing all of the modules and getting the integrated optics out of the network at that point in time. The other major project that we had to undertake was called a thin OADM to full ROADM. Initially, the network was built with these totem sites, and they really needed to be converted to ROADMs for this 100 gig to work. So again, that's a site-by-site conversion, a lot of maintenance work, a lot of time that it takes to get all those out of the network and fully converted. So again, that was another 2-year project to get all that taken care of. I'll get into the details of the totem versus ROADM in a minute here. So again, another scaling issue. As our network continued to grow, initially the inter-shelf communication was built upon an architecture of just a single OSPF area. And as time went on and as the network grew and more nodes were in the network, we started to have some troubles. We started to have some communication failures between the nodes, and we really started noticing that the routing tables were getting too big, too large for the shelves themselves to handle, and a lot of the routing update type information between shelves was bogging down that communications channel. So at that point in time, again, this was an instance where it really was kind of a partnership with the hardware vendor to come up with a solution. The solution that they had come up with was called Database Replication Service, which basically allowed them to break up the communication into multiple OSPF areas so that the shelves could communicate a little more cleanly and still still provide all of the PM data that we needed to run the network on a sort of day-to-day basis. Early on in the network's days, it was really optimized for 10 gig. At this point in time, though, in 2010, 2011, we're really scaling back the amount of 10 gigs that are on the network and looking to shift the optimization away from the 10 gig direct detection technology and towards the coherent receiver technology that was offered and going to be offered in 40 and 100 gig. And so one of the steps that we used to handle that was called differential provisioning. This basically allowed us to change the output power values of our transponders on the network. In order to get them to sort of cooperate well together, we needed to have this ability so that they wouldn't sort of interfere with each other. A lot of times we would find that we needed to have what are called guard bands or guard channels in the spectrum, which was basically just a gap between a 10 gig wave and a 40 gig wave so that they wouldn't interfere with each other. And unfortunately what that did is that cut down on our spectral efficiency for the time being. So it was really imperative that we really start getting the 10 gigs out of the network as much as we possibly could. And then basically at this time, all of our optical filtering was done through these totem nodes. And all that was is that it was a grouped filter that had 8 channels available, and you could daisy chain multiple filters in line to get the full use of the spectrum, so the 88 channels or thereabout. And previous to 100 gig, what we had always done is if you needed to come into a node and then change direction and go to another node, you would simply jumper a fiber connection between 2 filters and the signal would come in and pass through. Through the 100 gig trial, we learned that that was not going to be the way forward. We were not going to be able to do things in that mode anymore. And that meant that we then had to transition all of those locations and all of those nodes to full ROADM sites, which meant WSSs, 44 channel filters, and so on, so that they could handle the 100 gig transition. So that brings us kind of up to present day. We have transitioned all those totem to ROADM nodes on the core network. We're still doing that out at the edge as we push 100 gig into our smaller regional networks. We also are looking at basically expanding routes. So this year and next year we've got several new core-to-core links that will go in. And again, these are not trivial links. These are links that have between 13 and 15 spans inside of them. So they will be rather major builds. We've also incorporated new vendors into the network. This has helped on 2 fronts. Really, it's helped us keep up with the latest technology, but it's also helped us take advantage of the competitive differentiators between the vendors. They always want to try and get their foot in the door with something different and something new, and a lot of times those are great features to have, and so it helps to have them in the network alongside your incumbent vendors. We've also always sort of encouraged partnerships that help enhance the network in any way possible. So, I mean, that's really just a forward-looking process that we have. And then looking to the future. So like I said before, we're pretty much ready for terabit now. A lot of what we've seen in the 400 terabit range is short distance right now. So we've worked really hard over the last couple of years to remove regens from the network. We're not really looking forward to putting them back in. So we're in a spot where we're pushing hard on the vendors to make sure that when that terabit solution comes out, it is a long haul application, that it's not simply a metro play and we're going to have to spend a bunch of capital to go put regens back in the network, because we really spend a lot of time getting those out. Another technology that we're kind of looking at is this colorless, directionless. To give you a little background, colorless really, in today's DWDM architecture, you plug a transponder into a filter at a specific wavelength, and then you provision your transponder and it's set to that wavelength until you move that fiber jumper. In a colorless environment, you would be able to connect your transponder into a filter at the next available port, go back, and at a later date you can program your transponder to a wavelength, and the filter would be able to handle whatever wavelength you had programmed it for. So again, this gives you some flexibility to not have to be tied to a specific wavelength just because you're jumpered to those ports. Directionless is another similar idea, where today You cable that transponder to that filter, and that filter goes out in one direction. So you know I'm going east out of this site, and that's the only way I can go unless I move that fiber jumper. Directionless gives you the ability to basically connect those jumpers and provision them at a later point in time and re-provision them at a later point in time. So again, you've been given some flexibility as to where you're pointing the wavelengths. And then the last biggest piece for the future for us has been fiber. As most people know, the fiber that is in the ground is ancient. It's very old. And we've been in many talks with fiber vendors about what they're doing, what the new fiber is going to be, what it will allow us to do. We really are, in running this national network, we're looking for reach. We want fiber that allows us to space our huts farther apart, because when we're trying to go coast to coast, we really don't want to have a hut every 80 kilometers or so. If we can double that distance or come close, that would help reduce the cost to build out this national level network. And so we're in constant communications with them, trying to figure out what their next solution would be. And so that's pretty much what I had for you guys today as far as the state of our current 100 gig network. So if anybody's got any questions, please let me know.
All right, we'll take, literally, you get the only question, because we have to get to the break on time, I'm sorry. But will you be here?
Yeah,
So Benjamin will be here for
Here
any
I'll
other
be.
questions everyone has.
Chris Spears, Internet 2. So from the equipment that you deployed, it sounds like you're still on 100 gigahertz?
So no, we're currently at 50 gigahertz spaced, yep.
All right, I was wondering if you were, for your 1 terabit plays, you're trying to leapfrog and just go straight to gridless.
So yeah, that's something that we're kind of discussing. It's more in the hands of the vendors at this point. You know, it's really a decision that they're going to have to dictate to some degree to us. We're involved in the conversations, but from a technology standpoint, they can do what they can do, and when it's ready, we'll adapt to that. But yeah, I mean, certainly we've been looking at the gridless solutions and what that will entail for us.
And if anyone else is around that has a lot of other 100 gig pluggables like they do, I'd love to talk to you all.
Absolutely. So thank you very much again. We're going to go to break. One housekeeping note, I mentioned earlier the issue with the website. They're going to take the website down during lunch. It should be back up by 12:45. And the updated agenda will be posted at that time, and you'll be able to log in and vote and do whatever you need to do. We will be back here on time at 1 o'clock. For newcomers, I invite you to bypass the lunch immediately in the foyer and instead go to the Acamel boardroom, where we'll do the newcomers lunch as well. Any old timers who would love to come, we'd love to have you. Thank you, everyone.